Hi, this is part 2 of our video on chapter 1 topics. And in this video, we're going to cover chapter 1.2 and discuss more about how we can classify matter based upon its chemical composition. And there are two ways we classify matter based upon its chemical composition. And that is the sample that we're looking at a substance, or sometimes we call these pure substances, or is the sample a mixture? What we need to understand are the properties that help us distinguish either of these two features that we're looking at. Let's begin with the pure substance. I have listed here some of the features that help us identify if a sample is a pure substance. One thing that we look for in a sample of matter is it composed of one type of particle. Remember, the particle nature of matter is really important in how we as chemists understand about matter. If it's a pure substance and it's composed of one type of particle, then it's going to have a fixed composition and fixed properties that don't vary from wherever we collect that sample from. So there's no variation in either its composition or its properties. Let's think of a few examples that we might be familiar with. If you look at a neon sign, neon gas is an example of a pure substance. Table salt. Table salt is composed of sodium chloride, regardless of where we collect it from, and it has the same taste wherever we collect it from. Aspirin is another example. Let's look at a sample that we're probably more familiar with. Water as a simple first step. So it's a pure substance. As we said, water being a pure substance has a fixed composition. Water, in its pure form, is composed of molecules that have two hydrogen atoms and one oxygen atom, regardless of where we collect it from. If we collect it in the laboratory in a large Nalgene bottle, if we go to a store and buy Aquafina, pure water, it's composed of two atoms of hydrogen and one atom of oxygen. Fixed composition. There's my water bottle. It also has fixed properties, regardless of where we collect this pure water sample from. What we would find is that all samples of water have the same melting point. We'll learn more about melting point and boiling point, another property of water that's fixed. We'll learn more about these probably a little bit later in this course, or definitely you'll learn about this if you take Chem 1120. Another fixed property of pure water that we did discuss is density. So these are fixed properties of water, regardless of where we collect it from, regardless of the size of the sample. All samples of water have these and share these same particular properties. Now, let's think about neon gas that we've discussed just a few minutes ago. Neon. Neon is an example of a pure substance. Neon is composed only of one type of atom. And we would find this listed on our periodic table. Neon is an element. It's composed of only one type of atom. Let's draw a circle. There's a neon atom. We use a circle to represent the single particle. Now, water, H2O, is a compound. It's a compound. It's composed of two or more different types of atoms. Types of atoms or types of elements. So we can further classify pure substances as being either an element or, in the case of water, a compound. So let's begin with further classifying pure substances by discussing a little bit about elements. Neon is our first example. Elements are listed in the periodic table. If you go to the inside cover of your textbook, there's a copy of the periodic table. And elements in the periodic table are given abbreviations. Many of these abbreviations kind of easy to recognize. If you turn to your periodic table, H is the abbreviation for hydrogen. HE is the abbreviation for helium. So a lot of the elements simply use the first letter, and in some cases, they use the first two letters of the name of the element. Some of them aren't so easy. Cu is copper. Cu is from cuprum, which is the Latin name, the Latin derivation. So a lot of them have Latin names that we use the first two letters from their Latin name. Another one, silver, gold. Gold is Au, silver is Ag. Another one that we have that isn't Latin, W is for tungsten. W is Germanic, and I have on the PowerPoint a little discussion on tungsten, how we get the origin of the W is from wolfram. It's Germanic. So a lot of our elements, easy to recognize. Some of them have Latin, and still others may have other foreign abbreviations, such as tungsten. It's Germanic. So what you need to know for our first exam, this is our first little memorization, you need to know the first three rows on the periodic table. You need to know the abbreviation and the element name. So these include hydrogen, which is H, up to and including argon, which is Ar. I have a list of the first three rows. You need to know these. There's only one on there that's kind of difficult. If we look at the first three rows of elements on our periodic table, and we'll spend more time on the periodic table in chapter 3. The only one that's kind of tricky on there is Na. Na is for sodium. And as an exercise, look up where Na comes from, just for your own information. So that's what you need to know for exam 1, the first three rows and the abbreviations associated with the different elements. Now, we should also recognize that there are different conventions for how we write our elements versus our compounds. Now, let's look at two examples. N, lowercase o. The lowercase, in this case with the capital N, tells us that this is an element. This is the element known as nobelium. It's named after the guy that gave us the Nobel Prize. And capital O is different. Two capital letters tells us that this is a chemical compound. It's composed of two different elements, nitrogen and oxygen. Later, we're going to learn that NO has a name to it. We'll learn how to name chemical compounds. This is nitrogen monoxide. Now, wherever we collect a sample of nitrogen monoxide, it's always going to be composed of one atom of nitrogen bonded to one atom of oxygen. So let's discuss a little bit about our compounds now. Compounds. And let's return, as we were discussing earlier, our sample of water. So there's our aquafina. Now, water, any sample that we collect is going to have a particle, which is known as a chemical compound, that has two atoms of hydrogen combined with one atom of oxygen. And we'll learn how to write chemical structures and chemical formulas a little bit later. But this is how we represent the water in terms of its compound form. Now, what's important about water is that the compound itself has different properties in comparison to the elements that make up that compound. So let's think about some of the chemical properties of hydrogen and oxygen. Hydrogen and oxygen, well, hydrogen itself, if we have a sample of hydrogen gas, it's going to be explosive. If we have a sample of oxygen gas, it's going to be combustible. So if you have a family member that's on oxygen, you're not supposed to smoke around them because the oxygen gas is combustible. So what's important here are that the elements that make up the compound may have completely different properties in comparison to the compound that they form. Water is neither explosive nor combustible. The different elements that make it up in their elemental form share different properties in comparison to the compound itself. Now, as we said, there's its chemical formula for H2O. And as we said also, they have different properties. It has properties, that do not vary depending upon where we collect the sample from. So we said that a few examples, water, sodium chloride, and neon, they have properties, they have compositions that don't vary depending upon where you collect that sample from. We said another way we can classify matter based upon chemical composition are mixtures. Let's begin discussing mixtures. And let's help to understand how mixtures are different than compounds. So mixtures are physical combinations of two or more substances. So let's think about how mixtures differ than pure substances. So what's important about a mixture is that the individual components that make up the mixture retain their particular properties. So individual components have retain their unique properties. Another, mixtures don't have definite or fixed composition. In other words, mixtures oftentimes have variable composition depending upon where the sample was collected from. So a reality check. How do mixtures different than pure substances? Well, remember, mixtures, the individual components retain their own identities, their own unique properties. Compounds, they may have properties that are different than the components that make them up. Another thing is mixtures have variable composition. We might collect a sample of one mixture in one place and it might have a different composition than where we collect it from another place. Pure substances have a fixed composition. Regardless of where we collect that sample from, pure water is always H2O. Big important feature also, mixtures are the physical combinations of two or more substances. Pure substances are chemical combinations. They're formed by chemical bonds. And we'll learn more about the nature of chemical bonding a little bit later in this course. So let's think of a mixture that we might be familiar with. One of my favorites. Mixture, just to help us understand a little bit about a mixture. Coffee with sugar. This is an example of a mixture. Coffee with sugar. So as we said, one thing is that they have variable composition. One person might make their coffee sweeter than another person. One person might like their coffee stronger than another person. So they do have variable composition depending upon who made the coffee or where you bought your coffee at. Also, the different components retain their unique properties. Coffee has caffeine, which keeps us awake, and it also has sugar that tastes sweet. So those are examples of a type of mixture that we might be familiar with, coffee. Now, we can further classify mixtures. Remember, the more we classify something, the more unique we can identify it, the better we learn about it. We can identify mixtures or classify mixtures as being either homogeneous. A homogeneous mixture is uniform throughout. Or heterogeneous. Heterogeneous are going to be mixtures that are non-uniform. Later, we're going to learn that homogeneous mixtures are solutions. Heterogeneous mixtures, we're going to discuss them a little bit more in detail today to help us distinguish between these two ways we can classify matter. So let's think of some homogeneous mixtures we might be familiar with. A homogeneous mixture is vodka and water. If we take some vodka, which has alcohol in it, and we mix it with water, we're going to recognize that there's no visible difference in the appearance. We might look at a glass of water and a glass of vodka in water and not be able to distinguish between which is which until we actually drank it. An example of a heterogeneous mixture is going to be a situation in which we have orange juice with pulp. Orange juice has a liquid portion, pulp is a solid portion, and the pulp is a solid that's going to be suspended non-uniformly through that liquid sample. We also have gas that can be mixtures. Air is a really good example of a mixture that we're probably familiar with. Most cases, air is going to be a homogeneous mixture of gases. It's going to be a mixture of oxygen and nitrogen in certain defined percentages that make up the air that we breathe. If we go to a city and we collect air that's smoggy, well, that's going to be heterogeneous because there are solid particles that are suspended within that air sample. I have a picture here of a salad, And that salad, a good question here. Do you think it's homogeneous or heterogeneous? Since we're collecting different samples that are going to have different amounts of grapes versus strawberries, that's going to be an example of a heterogeneous mixture. So, important feature of mixtures is how we can separate them. So, since mixtures are physical combinations of different substances, we can separate them by physical means. If you take organic chemistry, you're going to learn that distillation utilizes the differences in the boiling points to remove one sample from a mixture and separate it from another sample using a physical property of boiling point. Another way we can separate solid mixtures from liquids is by filtration. Now, pure substances really can't separate them by a physical means. What we need to use is a chemical means of separation. One example that I have listed in today's PowerPoint is separating hydrogen and oxygen from water by using a means of providing energy in terms of electrolysis. So let's go over some samples, and let's this is a really good visual. I brought some fun samples, and let's classify these, our different samples. So this is our example. I like this. Let's do an example of classifying some substance, some forms of matter. We're going to look at a sample of matter, and then I'm going to let you stop the video and then answer a question. First one I'm going to look at, baking soda. Okay, and here's a hint. If you look carefully at the ingredients right there, it gives a chemical name. That is the name of this substance that we're going to learn more about a little bit later. So you could stop the video and think about baking soda. Question is it a mixture or is it a pure substance? If it's a mixture, is it homogeneous or heterogeneous? If it's a pure substance, is it an element or a compound? Stop the video and answer it. Okay, I'm going to go through the answer now. So you can stop it if you want, baking soda. So let's think about baking soda, and let's write down what was given on the ingredients. Baking soda. And our question is it a mixture or is it a pure substance? Now, if you noticed, I showed you the label. On the label, it said that the ingredients are sodium bicarbonate. Now, I could also give you a formula. You're going to learn more about formulas, but this is a hint. If I tell you something with a formula, that it has a formula of sodium, hydrogen, that's sodium bicarbonate. We have a name, we have a formula. Well, what this tells us is that regardless of where we buy baking soda at, it's always going to be composed of sodium, hydrogen, carbon, and 3 oxygen atoms. So it has a fixed composition. If you took a more advanced class, you would learn that this particular substance does have certain acidic and basic properties associated with it. And that would tell us that it does have certain chemical properties that are fixed. So it has fixed properties, fixed composition, fixed properties. And these would be the same regardless of where we buy the sample from. If you buy baking soda at Walmart, if you buy it at Food City, it's the same composition: sodium, hydrogen, carbon, and 3 atoms of oxygen. Baking soda is a pure substance. It's a chemical compound. It doesn't vary from one sample to another. Let's try another one. "70% rubbing alcohol, better known as isopropyl alcohol." So you can stop the video. Answer, is it a pure substance or is it a mixture? If it's a pure substance, is it a compound or an element? If it's a mixture, is it a homogeneous or a heterogeneous mixture? You can stop the video, and I'm going to answer it. Kind of tricky. The reason why it's tricky, they give you a name, but they also give you a percentage. So let's see. This is rubbing alcohol. Rubbing alcohol. It comes in a liquid form. If we would pour this out into a glass, it would look almost like water, but it has a certain odor to it. You would be able to smell it. And it's composed of 70% isopropyl alcohol. This is IPA, not beer. It's isopropyl alcohol. And the remainder of it is going to be water. So it's 70% that, 30% water. You could buy different combinations of it. I do believe I've seen 60, I've seen 30% isopropyl alcohol. Now, let's think about what's required for pure substance. Does it have a fixed composition? Does all rubbing alcohol always going to be 70 to 30? Some of them are going to be different. So they have variable composition. Another feature about it are the different components that make it up. This is composed of isopropyl alcohol. Isopropyl alcohol is toxic. You don't want to drink pure isopropyl alcohol. It'll get you sick, maybe kill you. Pure water won't kill you. So the different components retain their individual identities. So we should be able to answer. And one other thing. If we took some rubbing alcohol and we ran it through a distillation, well, IPA has a different boiling point in comparison to water. We could distill it, remove the alcohol portion, and retain our water portion and separate it by a physical separation. And that would be distillation. So with all that evidence, what do we think it is? Well, all this evidence leads us to believe that rubbing alcohol is a mixture. They would have variable composition. Percentage of alcohol to water might be different depending upon where we get it at. The different components, the alcohol component and the water component, retain their individual properties, and we could separate it by a physical means of distillation. So this is an example of a mixture. Now, if we looked at isopropyl alcohol, rubbing alcohol, if I poured this out, I would recognize that it's a liquid that looks almost identical to water. We can't really see any difference. So this would be an example of a homogeneous mixture. So far, so good. Let's try one more. Now we're going to have some fun. Bottle of beer, IPA. This is different IPA. So what do y'all think? Okay, do it yourself at home. Take a bottle of beer and open it up. Try it. If you have a bottle of beer, it'll work. If you have a bottle of soda pop, it'll work also. Try it. And let's think about what would happen if we take a sample of beer. And what we would recognize if we pour some beer out, beer has alcohol in it. It has yeast. It has malt. It has a lot of other things. There's sugars in there. If we take beer and we pour it out, into a nice mug. There's our mug. You're going to get foam on the top. And you're probably going to get some foam in here. And down the bottom, you're going to get a yellow appearance like that. That's our mug of beer. That's the best I can do. I was going to pour it out, but I'm not drinking right now. I don't want to waste a good bottle of IPA. Now, what we should recognize is that beer has alcohol in it. It has sugars. It has yeast. It has malt. It has a lot of different components in it. So it doesn't have a fixed composition. Some beers are 7% alcohol. Some are 4%. This one is 6.3% alcohol. If you want to look at that and verify it, 6.3% alcohol. So different samples of beer have different percent alcohol associated with them. So what this tells me right away is that beer is not a pure not a pure substance. Beer is a mixture. Now, as I said, if we poured the beer into a mug, there's going to be a separation. The liquid portion is going to be on the bottom, and through it are going to be bubbles, and on the top, you're probably going to get a nice head on that beer. There's a separation of different physical states of matter. We're going to get carbonated bubbles in it along with liquid, and this separation of physical states leads us to believe that this is a heterogeneous sample. So those are a couple of examples of how we can distinguish different samples of matter based upon how they look, how we can separate them, how they taste, how their compositions may be different or identical between where we collect them at. So we're going to go back into chapter 1 on Friday, and I'll post a few other videos to help you. Thanks a lot.